Okay, welcome everyone to part 8 already of what is quantum topology. We are still kind of trying to recall what categories are. So really in these lecture notes I kind of assume that you have seen categories at least in some way or form. So I'll go through it further rather quickly because we want to jump into more interesting and enriched categories. But anyway, right now we are still in the category part. And if you talk about categories, you need to talk about functors, right? So recall a category essentially, well, it has objects and morphisms, objects and morphisms, two type of things. And the only thing we really have is composition. And their identities, sure, fine. But the only thing you really have is composition, right? That's about it. The category is a kind of a not very difficult concept, objects, morphisms, and composition of morphisms. That's about it. So if you want to talk about a morphism of categories, you should kind of do something to objects, you should do something to morphisms, and you should preserve composition. That's essentially what you have to do because that's the only information you're given, right? So that's has then to be the correct answer, or kind of has to be the correct definition. So what could it be, right? The functor is just this name for a map between categories. Functor, I'm not quite sure where that comes from. It's kind of a meaningless, a name without any real meaning. So it comes from the original paper of Eilenberg and McLean. And I can just pull it up. That's not what I wanted to do. It originated in the 1940s, right? Eilenberg and McLean, as I said. And they were literally trying to describe some operations in algebraic topology. And they came up with this kind of non-saying name categories, and they came up with this non-saying name functors, and they came up with this non-saying name natural transformations, which we will see later on. The main focus, by the way, from the beginning was on natural transformations and functors, not so much on categories, right? Category theory should take itself serious, so category shouldn't be the main player of category theory, right? Category theory is about relations, not about objects. So categories are not the main players of category theory. Kind of interesting. More important are actually those functors. So here's my category, and it should map an object to an object, a morphism to a morphism, such that like commutative diagrams are preserved, right? That's the only thing we have in a category, so that should be the correct notion of a morphism of a category, right? So from a bubble here to a bubble here, such that one of these little diagrams, composition Fg equals H, is preserved. Fg equals H, right? So that's what it should be. And the standard example you can have in mind is between our two best friends, vector spaces and sets, there's a forgetful map. Just forgetting that you have a vector space. Just forget that you have a vector space. Very easy. It sends an object to an object. It sets a vector space to a set, just to the underlying set. Forget the linear structure. It sends a linear map to a map by just forgetting that you have a linear map, and it preserves composition in the obvious way. So it's kind of a standard example of a functor. In some sense, set is a forget version of vector spaces. Forgetting is always easy. There is, turns out, a map in the other direction, but not today. It's called the junction, the free vector space construction. And the functor is then what you think it is. A composition is preserved. And there's this unitality axiom, so units will also go to units. So functors, you associate something to every object, and you associate something to every morphism, such that composition is preserved. It's really like this type of picture, right? Y goes to f of y, f goes to f of f, x goes to f of x, such that this little f here goes now between those two, and then composition is preserved. We have identity functors, compositions of functors are functors, functors form a monoid because compositions of functors are functors, and actually they form a category. Well, the category takes itself serious, and we'll see that later on. No, not now. And categories should form a category. Category theory takes itself serious, so there should be a category of categories with forgetful functors between them. There are some set theoretical issues which I really don't care about, but essentially the slogan should be everything forms a category, including categories. And again, the focus should be on the relation between categories, which in this case are the functors between categories. Anyway, I hope you enjoyed this video, and I also hope to see you next time.